for this problem, what we have is an ionic compound, which is actually dissolved in water, and it is fed at 1,100 pounds mass per hour, and it was evaporated so that the outlet liquor would be 40% concentration. The steam is fed at 120 degrees Celsius, and then there are additional data here. It says that the operating temperature or pressure for our evaporator is 101.325. That's actually 1 atmosphere. And then the solution is charged in a 3-inch inner diameter and 100 feet of pipe. So the question is, what is the steam or steam requirement for this problem? And then we need to determine the power requirement as well as this total heating area. So there are 3 questions right here, and let's just illustrate the problem first. Now I would like to emphasize that this is not how a forced circulation evaporator looks like. It has something like a pump here so that the feed we would be assured to have this for circulation. But as what I've told you before, evaporation would always employ the same concept of the feed and then the steam, and then it will just go out as liquor, and then the steam would be either condensed or actually not. So they employ the same concepts and principles. That's why you could just use the same general idea of evaporators. So let's add something like the heat exchanger. So we're done with the figure, and now let's add all the necessary components. So we have a feed, and then we also have the liquor. So it's right here, and then we do have the vapor that is being released. So that's it, and then finally we have the steam. So the steam is actually saturated, so unlike the one that we did before, so this one is saturated. So when we say saturated, the maximum amount of the substance is actually dissolved on that certain solution. So if that's the case, then this is actually related to a temperature in a way that for every pressure, there should be an accompanied temperature for it to be saturated. Okay, so I think that's all for our figure. Now let's label some parts here. We know that the the feed rate is 1,100 pound mass per hour. Now we'll be using English units to solve this problem. So we have the feed, so that is equal to 1,100 pound mass per hour. And then we have this feed at 20%. So that's 0.2 for the fraction. And then the density, at the temperature of, so we have 20% at a feed temperature that is equal to 20 degrees Celsius. So we also have something here. It's 190.538 as a density, but I won't be adding that on our figure because I'll just tell you something later. And then we proceed with the steam. So this is the steam. Let's just label it as S. And then we need to give its condition. It says here that it's saturated. So it's saturated, and that is at 120 degrees Celsius. So this is our condition for steam. And you should always be happy when the steam is saturated, because it minimizes a lot of interpolation from the Paris handbook compared to the superheated or those that are actually not at saturation condition. Anyway, so we move on. So that's the steam. The evaporator is operating at 101.325 kilopascal. So the pressure at this vapor chest is 101.325 kilopascal. So this is the vapor chest. Okay, so that's actually 1 atmosphere. So let's just write here 1 atmosphere. Okay, so first things first, we need to calculate the steam requirement. To do that, we need to first do the material balance. So let's have it first, and then we could calculate for the heat requirement in this case. So we start with the overall material balance. This is just a single effect, but it has a boiling point for this case. So let's just have this as with BPR so that we don't forget it. Okay, so OMB is always this F is equal to L plus V, wherein F is equal to 1100 and L is not known as well as V. I forgot to write V here, so let's just write the vapor. Okay, and then for the component balance, we know that F XF is equal to L XL. I actually forgot to write 0.40 or 40% because it's stated in the problem. So don't get confused with this. It says here that the solution is fed at 1100 pound mass per hour, evaporated so that it gets 40% at the liquor. So this 40% means that it is 40% at the liquor and not 40% at the vapor, because that would typically be incorrect. Anyway, so we have the feed, that's 1100, and then we multiply this with the XF, and that's 0.20. That is equal to L and then 0.40. So in this case, we will be getting a value of 550, that's pound mass per hour. Okay, and then knowing that we have F is equal to L plus V, then therefore the vapor from this balance, we could say that that's also 550 pound mass per hour to make up with this 1100 of total feed. So that's it for our material balance, and now we proceed with our heat balance. Okay, and before I used to solve for a heat balance wherein I used actually the energy balance. Now we proceed with enthalpy first, because that's basically how unit operation should be done. And as what I've said before, you should be using this only when you have enough data or information. And if you would look at this problem, you might be saying that I don't have enough data because we don't have any something like a heat of solution for the feed, for the liquor, so we don't have them. Well, that's true for this sentence, but we can use the table at Paris Handbook, because there's a special table in your Paris Handbook where they give an enthalpy concentration diagram. So this enthalpy concentration diagram is very important because it actually gives us the direct values of our F enthalpies. So going back, we have this balance. So we know that to balance this, we have this F and then the enthalpy of the feed plus S and then the enthalpy of the entering steam, that is equal to the liquor and then its enthalpy plus the vapor and its enthalpy, and then finally this S, and then assuming that it's condensed. And then when we try to redefine this or do some transposing of the unit, we get H sub S minus H sub S right here, and then that is equal to L and then HL plus VHV and then minus F H sub F, wherein this can be reduced into lambda S, or the latent heat of vaporization or condensation. Okay, so this is our final form. Okay, now let's look for our HL, HV, HF, and lambda S, because that's typically what we need. We already have this L and V, and of course our feed. So to get S, we need to find these four unknowns. Okay, so we go back to Paris Handbook, and then let's check on this chapter 2. And then as you can see here at your thermodynamic properties, there are some enthalpy concentration. As you can see here, for example, this ethyl alcohol or ethanol, there's this enthalpy concentration diagram, same as for hydrogen sulfide. So some compounds have this enthalpy concentration diagram, but of course not all of them. And fortunately, we have for sodium hydroxide, and that's where we will be using this. Okay, now let's look at this concentration, weight fraction, and then enthalpy diagram for 1 atmosphere for sodium hydroxide. So this was taken from McCabe, and then of course with permission from them or from him, I don't know. Now this is very important. You can use this chart only when the total pressure is 1 atmosphere. Actually, some of the books are using this even the pressure is not 1 atmosphere, but it is said in this Paris handbook that you should be, I mean, it's not that you should be using, but it is clearly stated here that this is a diagram when sodium hydroxide is, has an aqueous solution with 1 atm as the operating pressure. That is because, concentration and then this enthalpy tend to change with respect to the operating pressure, because that's basically what happens, because the temperature is actually and the pressure are the determining factors for our enthalpy. That's why if the pressure changes, so should the enthalpy. That's why you should be strictly monitoring this condition. And going back to our problem, as you can see here, we actually have 1 atm, so we can freely use this. But if not, then we proceed with the heat balance. And the good thing about this video is that I'll be showing you the other way of using not this enthalpy balance, but using this energy balance. Okay, it's just that I want to show you how fast is this our computation when we use this enthalpy balance. Okay, so going back, we need to find H sub F first, because that's the easiest one that we can obtain from this. So I'll be using a different color, and let's make it orange. So H sub F, so that we get some complementary colors here. So H sub F, it says here that it's a concentration enthalpy diagram. So what you need here is the concentration or the weight fraction of your sodium hydroxide, and in this case that's 20% weight. Now, if the problem states that this is actually in mole fraction, then you should be converting that. But since this is already weight percent, so we can use that. Now, we need to take a look at the temperature here. It's like when you have this concentration or weight fraction, you move to the point wherein you would intersect this temperature, which is the temperature of the feed. For example, if it is feed, then that's the feed. If it's the liquor, then that's the liquor. So in this case, that's 20 degrees Celsius. And this is in Fahrenheit. We need to convert this 20 degrees Celsius in Fahrenheit. And from this, we know that 20 degrees Celsius, so that's the temperature of the feed, is actually equal to 68 degrees Fahrenheit. Okay? And actually, I'm using just the shift convert in your calculator. So if you don't know that, just use shift convert and then number 38. So it gives you directly to degrees Celsius and then Fahrenheit. So that's 68. And then, since we have 68 degrees Fahrenheit, so going back with this, so 68 degrees Fahrenheit is, we know very well that this is 50 degrees Fahrenheit. Going up, this is 60, 70, 80. I hope you can see the hand. So I'm panning from this screen. So we have 60, 70, 80, 90, and then 100. You can check on that. That's 110, 20, and then 50. So that's just 10 intervals. Okay. So with that, we know that we start with 0.2. So we start with this 0.2, and then we know that this is 40, this is 50, and then this is 60, and then this is 70. Since we need 68, 68 is just around here, just below 70. And then lastly is that you project this horizontally. So from this point, you project that horizontally, and then you should be able to get the enthalpy that is that corresponds to that concentration and then temperature. So don't get confused with these curves. They are temperature curves. So you shouldn't be something like, okay, I'm gonna trace that and then that will be the answer. That's not the case. You should be projecting that to the left. So the answer would be something like at the middle of this. Actually it's not the middle, but we can just divide all this into 50. So that's 0 plus 50 divided by 2. So that's the middle section. So that's around 25, I think. But let's just count. That's 10, 20, 30. That's 30. Because that's 40 and then 50. Okay. Actually, this intervals is not actually for the enthalpy, because as you can see here, we don't have any. But as you can see from this figure, it actually divides the whole interval in equal sections. So you can actually use that. But remember that that's for our temperature. So anyway, we have 0 and then 10, 20, 30. So our heat of formation, our heat of enthalpy of the feed is 30. That's a British thermal unit per pound mass. Okay. Now we proceed with our liquor. Now we know that our liquor has a temperature which is actually the vapor chest temperature plus the boiling point rise. So you should be evaluating our HL at the temperature of course, our liquor temperature. But to do that, we need to determine first what would be our liquor temperature. Since we have already known how to use this During's chart, we call that During's chart, the one with a lot of vapor. I mean, with a lot of lines that we can determine the boiling point rise. So we call that the During, not Duling, During's chart. Okay. So we go back to that and then let's find the final solution temperature. So that's for that's on chapter 11 for the discussion of evaporators, and that's around here. And as you can see here, there are a lot of evaporators. There's this type, and I think this is the forced circulator, letter A. Correct, A. And then we also have B. B should be forced also. Okay, yes, B. But this is submerged type. That's why. Anyway, so this is the forced circulator. Actually, as you can see here, it's almost like the same. It looks the same from my drawing. The only difference is that it's kind of long. It has actually a long tube. Unlike this submerged, in a way that the heat exchanger is kind of at the separated from the evaporating chamber. So anyway, it's not my concern. So let's go to the figure. Okay, I didn't erase this. Anyway, so so let's go back with this and let's check on the conditions right here. We know very well that at this point, you should know that we'll be using 40% instead of 20%. I have to make that clear again. In order to find the boiling point rise, you should be using the concentration at the liquor and not at the feed. The reason is that we're actually concerned with the solution on the inside, and that happens when we're boiling it. So basically, if we're considering the inlet at that point, then we cannot account all the changes that would happen during this process. That's why we would always take on consideration the final output, which is this 40%. So that's 40% concentration, and then that's sodium hydroxide. Okay. In this case, we're not given with any solution temperature because that's what we're looking for, but we're given with the operating pressure, and we know that the operating pressure would give us the vapor chest temperature. So from P is equal to 101.325 kilopascal, and that's simply 1 atm. 1 atm. We know very well that this is the TV, and this temperature at the vapor chest is, of course, that's 100 degrees Celsius because that's 101.325 and it's saturated. So I hope you already know that because, well, that's how it works for 1 atmosphere. So going back to that figure, so that's 100 degrees Celsius, and this is actually equal to 212 degrees Fahrenheit. So we already have this TV. Now, so the first step that we need to do here is to assume a certain value from 212 degrees Fahrenheit. So I'll be doing something like from 212 degrees Fahrenheit, let's assume a certain solution temperature. Let's say let's always choose the closest one, which is typically, if it's 200, right? I mean 212, so it's around here, and then 220 could be an answer. So let's take 220. So in that case, the BPR is 8. That's the assumed boiling point rise. So we start with 220. We project this to sodium hydroxide. So that's it. And then we go back to its final percentage. So that's 40%. Okay. And as you can see here, I'll be going beyond this line. Okay. So as you can see here, the boiling point that has been obtained from this crisscross, is that crisscross, that those lines is actually 40, this 40, so around 47. So that's a really high compared to your assumed, which is 8. So with that, let's use 47 instead, because that's what the graph gave us. So that's 47. And if it's 47, then we add that to 212. So we have the temperature that is 259. So in this case, T is equal to 259. So that's quite a really huge leap from this initial. So that's really close to 260. And then let's make it closer. Okay, so that's 259, and then let's project this to sodium hydroxide. Okay, and then this line, let's project that from this point, and then 40%. Okay, as you can see here, the changes is not really that big, and it is quite very close to the value. This is around 47. I mean, BPR of 47 assumed, and as you can see here, the value is, yes, almost around 47, but I think that's more on 48. Well, that's just my my assumption. So T is equal to, I mean, the BPR is actual is around 47. I mean 48, I think. So it's 48. So with that, let's use 48 instead. So if we use 48, then that would be equal to 260 degrees Fahrenheit. Okay. So if that's 260, then it's around here. Okay. So if it's 260, actually the movement, I mean the line didn't move that much. And as you can see here, that's almost like perfectly fitting this line as well. So in this case, we know that BPR is 48 degrees Fahrenheit. So I hope it was clear to you how I did that. It's just you assume a value that is above the vapor chest temperature, and then the first answer would somehow give you an idea of how, I mean, of what is the answer. So that's basically 47, I think, on our first try, and then use that for the second trial, and you should be getting the closest possible answer in your second. Most of the time, the students are able to get the answers by after some 2 or 3 trials for this. So, and that's not really difficult. So we have 48 degrees Fahrenheit. So that is 48 degrees. I mean, our BPR is 48 degrees Fahrenheit. Okay. Now, let's try using this formula from how do you call them? This form. Sorry, it should be in the previous pages. So let's use this formula from Miranda and further. Okay, so that's BPR is equal to 104.9, and then n sub 2 raised to 1.14. So let's use a different color. It says there that the BPR is equal to 104.9, and then n sub 2 raised to 1.14. Now this n sub 2 is the mole fraction of your liquor. So let's try using 40% in this case. So we need to convert that into mole fraction. So let's have this XF, I mean XL mole fraction, that is equal to, we have 40 grams of, let's say we have 40 grams of sodium hydroxide, and then we divide, of course, to 40 grams, that's 1 mole, because that's the molecular weight of sodium hydroxide, and then we have 40 over 40 as well, and then since it's 40, we have 60 for this, and then divide by 18. So we would be able to get an XL for the mole fraction of 0.2308. Okay, and then using this formula, the BPR would give us a value of 19.715 degrees Celsius, and then to convert this to Fahrenheit, let's multiply to 1.8. This would be equal to 35.4871 degrees Fahrenheit. So as you can see, the BPR obtained from this Miranda and then from the During's chart is actually, they're actually quite different. they differ by around 13 Fahrenheit units. So what will you be selecting? So in this case, you will be using the one obtained from the During's chart. So let's cross this out. Why is that so? Because this figure is a correlation obtained from atmospheric pressure boiling point. Now, it is true that our problem is also obtained from the atmospheric boiling point, but this expression is actually showing us the approximate BPR losses in a way that this is just an approximation and a correlation. But unlike these radiation and then convection, the During's chart is more accurate than using this correlation that they have already obtained. So we will always try to stick with what is more accurate, because as you can see here, this is what this correlation did, just to give you an idea of how it worked. So we have a lot of ionic compounds right here, and then they try to like generate a general line from this. I don't know if it's something like a curve or what, but as you can see here, that's just a polynomial function of some rational degree. So it's like they used one line to represent all of these variables, because that's, as you can see here, we have this some compound, and then as you can see from here, it somehow lies at a certain point wherein they're actually lying on along the lines that I have drawn. So basically that's what they did. But how about for this calcium chloride, sodium chloride, and then this sodium hydroxide? They're actually quite far from this line, so you couldn't be using that for such for those expressions that we have. But as you can see before, when I tried to solve for a value of that using this equation, KCl, I think that's KCl, because KCl is kind of, you know, close to this line, as well as this sodium chloride, I think. Is that sodium chloride? Anyway, that's how it worked for this, because the idea is that they just correlated it using a single line. And this line, even though you don't get to have the decimal points, I think using this would be much more accurate than using this BPR. Okay, so let's cross this out. It's not included. Okay. Anyway, so let's proceed. So we already have this BPR. Let's just remove this and this, because this is quite messy. Okay, so the BPR is 48, and then we can go to the finding the liquor temperature. So with this, we already know that TL is equal to TV plus the boiling point rise. And in this case, that's 212 degrees Fahrenheit plus 48 degrees Fahrenheit. And now we have our liquor temperature, that's 260 degrees Fahrenheit. Okay, so that's 260. And now we go back to this enthalpy concentration diagram and take a look at 260 degrees Fahrenheit using our HL at 40% concentration. So we go back to, let's remove this, because it might get removed when we take the board exam. Okay, so don't ever write something on your Paris handbook. Don't take the risk. Okay, so let's go to physical chemical properties, and then enthalpy concentration diagram of sodium hydroxide 2-403. Okay, so we have 0.4 and then 260. So that is 0.4. Here is 0.4, and then 260 is around here, because this one is 250. So basically this 250, and then therefore if you trace that graph 250, and then you go above that, so that's 260. So basically this is the point. This is 250, and then this is 260. Okay, so that's it for 260. This is 250, then 260. Don't get confused with that. And then let's extend this line further. Okay, and there you have it. It's actually at the very middle of 250 and then 200. So if you take the middle of this, you could say that that's 225 BTU per pound mass. So therefore, our HL is 225, that's British thermal unit per pound mass. Okay, so that's it for our chart. And then let's have HV. Now HV, we've got no problem with this HV because that's actually obtained from the fact that we have a vapor chest and we can actually solve for it. But remember, this HV is actually equal to HV at the vapor chest, and then we add, because it becomes superheated after some time, because we have the boiling point rise right here. So you need to add the specific capacity of the vapor and then multiply that with the boiling point rise. So this is the new equation for this HV. So that happens again because during this boiling, we could see that the solution should have been boiling at 101.325 because that's the vapor chest, that's the operating pressure. But because of the concentration of this sodium hydroxide, and that's 20%, it gave us an increase in final solution temperature. That's why if we would account the enthalpy at the moment when the temperature is reaching this operating pressure, the vapor should have been escaping. So that's the amount, that's the enthalpy of that vapor. But because it increases further at that pressure we're in, that's the operating pressure, we should be accounting that sensible heat at the moment when we reach the final solution of our temperature. So I hope I made it clear on that note. So whenever you have this HV, you take the heat of vaporization at that certain temperature, so, and then you add the sensible heat of the vapor times this boiling point rise. And the good thing about this is that it can easily be found. So you just take the HV at this vapor temperature. So you go back to the Paris handbook, and then you just take the thermodynamic properties, and then at 101.325, that's 212 degrees Fahrenheit, you should be getting your HV. And the HV that you would be getting, or the enthalpy of vaporization, is 2677.7683, and that's joule per gram. Okay, and then this is equal to 1151.0562 because that is what we need in British thermal unit per pound mass. Okay, and then finally we need to take this CPV BPR. So we need to add here this CPV. I hope you don't get confused with this. Okay, so this is for the TV, and then we need to add this CPV BPR. So we have the specific capacity of the vapor, of water vapor at any, at the condition wherein it is superheated. So that's 0.46. This is British thermal unit per pound mass, and then degrees Fahrenheit. Okay, so that's 0.46, and then the boiling point rise is 48. So that's it. And the final HV that we have is this value. Okay, so you might get confused with this with what happened here, and the easiest solution that you can do here is just you take on the final temperature, which is 260 degrees Fahrenheit, and then try to find HV from that. You should be getting the same answer. So let's try to do that here. So we have chapter 2, and then thermodynamic properties of water. So as you can see here, we have 100 degrees Celsius at that point, wherein that's the vapor chest. But accounting the boiling point rise, we should be getting something like a temperature that is 382.04. So we'll be interpolating at that point. Not in saturated. Okay, so don't forget that, not in saturated, because that's already a superheated vapor. So you should be interpolating somewhere here, okay, at the single phase property. So you take on this 0.1 atm because that's kind of close to 101.325. But if you want to be closer with this, you can just try to double interpolate in this point. That's why I used that previous procedure because that's quite easier than double interpolating, but let's do it again in this case. So you have 382.0388889, so let's use that to interpolate in between these values. Okay, so what we obtained from our Paris handbook using just the interpolation from 1.1 megapascal, and then we have this final TL that we have is actually equal to 2696.127447. And then if you would divide that to, if you would like to convert that in terms of British thermal unit, then you should be getting 1158. So you should be getting 1158.9480. So this is the value obtained from using this HV and then accounting the sensible heat obtained from the boiling point rise. And this one is obtained from using just the direct TL, but using 0.1 megapascal. So probably the difference that this is kind of low because the temperature that I use is actually 0.1 megapascal and not 0.111325. So it can still increase when you would be using double interpolation. So I'll leave this with this value, and then of course I will be deleting this because this is the less accurate one that I did. Okay, but anyway, you can do that as well in your solution. So we already have this HV, and now let's try to find this lambda s. And to do that, we need to find our capital H and then S and then the small s and then this lambda s. And we've got no problem with this. We already obtained that. It doesn't affect our temperature because that's the steam. It flows on the other side of the tube. So we have HS, and knowing that it is 120 degrees Celsius, this is actually equal to 393.15 Kelvin. Okay, so using this 393.15, so for our enthalpy of the steam, we have 2708.1436, that's joule per gram, and then we have 504 for the liquid phase, so that's 2588, and then joule per gram. Now if we subtract these two and then convert it to the required unit, which is in BTU per pound mass, what we'll get is 947.3543, and then that's in BTU per pound mass. Okay, so we've already finished finding all the unknowns that we have using this enthalpy balance. Now let's try substituting all of them to the equation that we already obtained from this. So we will be using this as lambda s is equal to is equal to LHL plus VHV minus FHF. Okay, so S times 947.3543, this is equal to our L, and the liquor is 550. So that's 550 multiplied with, I think that's 225 based on our figure, and then we have plus 550, and then HV is a capital H accounted with the boiling point rise, so that's 1173.1362, and then we have minus 1100 times our heat of enthalpy of the feed, which is 30. I always say heat of formation. By the way, this heat of dilution is not included in our computation because typically it's so difficult to identify those values. So finally, our answer is 776.8740. That's pound mass per hour. Okay, so this is how you solve for this problem with boiling point elevation. And now let's try solving for this again using a different approach. And instead of using enthalpy balance, assuming that we don't have enough data, or assuming that the pressure is not actually 101.325, that's 1 atm, assuming that it's not the case, so we can't use this graph or this enthalpy concentration diagram, So let's try using the derived form in terms of energy balance. So again, we start with this S lambda S equal to F HF, S lambda S equal to LHL plus VHV minus FHF. And then after some time, using the fact that Cp of the feed is kind of equal to the Cp of the liquor, we can therefore say that S lambda S is equal to the feed and then the specific heat capacity, and then setting our datum temperature equal to the boiling or the vapor chest temperature. So we have CPF is equal to T of our liquor minus T sub L minus T sub F, and then we add the vapor, and then in this case, since we should be using lambda V, so we should be adding lambda V, and then we need to add the specific heat capacity of the vapor, accounting the boiling point rise again. So that should also be noted, because it's the same explanation as I said before. The vapor the vapor should be escaping at that pressure, but since it's actually increased, so the superheated vapor must be considered. Okay, so that's it for this balance, and now let's use this to be able to find this value of S. Now, for this case, we need to find this. We already know that TL and TF being 260 for TL, and this lambda V, we need to find this H sub L because we already have H. So, how about this specific capacity of sodium hydroxide? Now, if you'll be looking at these organic compounds right here in this section 2, you won't be able to find the sodium hydroxide, unfortunately. But the good thing about it is that under the specific capacities of aqueous solutions, you can see right here that there's sodium hydroxide. Okay, and where is this? That's it, sodium hydroxide at 20 degrees Celsius. So we have sodium hydroxide right here, and then it says here that we need the mole percent of that sodium hydroxide in order to be evaluated, and then this is in calories per gram degree Celsius. Now, if it's mole percent, we know very well that this X sub F on the feed would be, so if we'll be using our X sub F, and then that's mole fraction, we know that that is equal to 20, and then we divide this by 40, so 1 over 40, and then that's 20, and then over 40 plus 80 over 18. That's our mole fraction, and this would give us a value of around 0.1011 mole fraction. Okay, so using this 0.1011 or around 10.11%, let's interpolate that value from this figure. So we have here 0%, 0.5%, then 1%. That's 9.0%. So we'll be interpolating in between this 9.0 and then 16.7. So the answer is 0.83 and 0.3. Okay, so our specific heat capacity of the feed is, let's just write it here. The specific capacity of the feed is 0.8303, and that's, the unit is actually calorie per gram Kelvin. Now, if you would want to convert this in terms of English unit, you would also get the same answer. So we have 0.8303, and then that's British thermal unit per pound mass, and then degree Fahrenheit. Okay, so we'll be using the same value for this. So we already have CPF, and then TL, TF. We also have the feed, and then the vapor. So we just, and then of course this lambda S. So we need to just find this lambda V, and to do that we need to take on the value of this H sub L. H sub V from the Paris handbook is equal to 180.3398. That's British thermal unit per pound mass. Okay, so knowing this value, we can now solve for our lambda V and then Cp of the vapor and then VPR. So let's just substitute all of these values. So we have S, and then lambda S again is, from here we have 947.3543. So 947.3543, and then this is equal to our feed, that's 1100, Then our Cp is 0.8303. Then our temperature of the liquor, which is the final solution temperature, that's the boiling, we have 260 degrees Fahrenheit. And then our feed is 20 degrees Celsius. That's when converted becomes 68 degrees Fahrenheit. Okay. And then we add the vapor, that's 550. And then we have this lambda V. So from our HV, we know that that's 1173.1362. So we have 1173.1362. So we have 1 and then 362. Then we subtract this 180 from based on our Paris handbook, and then we add the specific capacity at the vapor at English unit, so that's 0.46, and then the boiling point rise is 48. Okay, so this is our final equation. So solving for this, we'll be able to get S. So from this, the answer is 774.3052. That's pound mass per R. Okay, so as you can see here, we really have a close value using either way. We have the enthalpy and this heat balance. This is easier done when you have all the values of necessary values, but of course when you would be having different enthalpy concentrations available to you, this one is a lot easier. But we already proven that we will just get the same answer. And now let's talk about this next question. We have to determine the power requirement, and power requirement is kind of easy to determine. You just have to find your Q. So for number 2, we just need to find Q, and then Q is equal to S lambda S. So we just have to take this S, that's 774.3052. That's so we have this 774. Let's just use the first one. So we have this 776.8740. So we have 8740, and then that's pound mass per R. And we multiply that with our lambda S, so that's 947.3543. And then that's in BTU per pound mass. Now we cancel this pound mass, so we're left with the unit of work, that's BTU per R. So Q is equal to 735,974.9245. That's British thermal unit per R. Okay, so this is our answer for the second question. That's our power requirement. And basically this power requirement is actually supplied by the steam. Now, for the last one, we have the third question is, what is the total heating area if U is equal to 1252? Actually, this should be Fahrenheit. My bad. Okay, so that's it for our, let me just fix this. Okay, so going back, we have this 1252 U, which is actually the overall heat transfer coefficient. So for number 3, we have U is equal to 1252 British thermal unit per R, and then that's feet squared degrees Fahrenheit. So as you can see, the unit is kind of the same as our the heat transfer coefficient. So this is our U, and then remember, I used to tell you that Q is always equal to U and then A delta T for our evaporators. And then this delta T, in single effect, no boiling point elevation, we have Ts minus Tv. But if we have boiling point elevation, this is equal to Ts minus Tl. Okay, and that's the boiling point of the solution. So in this case, we have Q, which is equal to 735,974.9245 British thermal unit per R. That will be equal to our U, that's 1252 British thermal unit per R, and then feet squared degrees Fahrenheit. That is multiplied with the area, and that's what we need. And then delta T is simply the difference in and then the steam and then this solution temperature. So the steam is actually fed at a temperature of 120 degrees Celsius. In degrees Fahrenheit, this 120 degrees Celsius is equal to 248 degrees Fahrenheit. So we have 248 right here. So we get 248, and then we subtract this by TL, which is actually 260 degrees Fahrenheit. Okay, so as you can see here, we have a negative value here. And how is this possible when we have actually the steam temperature that should be the highest? Now, this is a very hypothetical scenario wherein the final temperature of the solution is kind of larger or higher than our steam temperature, and basically sometimes it shouldn't be happening in that way. But based on the During's chart, we did our calculations, and that we have 40% right here. So we already obtained this kind of delta T. For such cases, when the temperature gradient becomes negative because of the difference in the surface, the steam and then the liquor, you should be interchanging this so that you should be getting a positive answer. So in that way, I will be able to get an answer that is in terms of positive value. So the answer is 48.9866 feet squared. Okay, so now again, I would also like to tell you that this should be interchanged because in general, we should be using TS minus TV or TS minus TL. But in a case like this, the liquor temperature became higher than our steam temperature because of the fact that it really had a huge boiling point elevation because of this 40%. So in that way, the liquor temperature would be higher than our steam. So we can't do anything about it. It's just that on a general note, if it becomes negative, then you make this positive. Okay, so that's the thing that you can do right here. Because of the calculations, we can't do something about this. Steam economy natin naman is hindi naman siya magiging greater than 1. Because as you can see here, we have 550 for the V and then 776.87 for the dito. Basically, less than 1 naman siya. So, tama naman siya. It's just that in this scenario, the temperature gradient of this steam is kind of mas malaki pa yung final temperature ng ating liquor, which is that's what happened. So, okay? So, that's it for our evaporation. I hope you've understood things here, and on the next videos, I'll be doing something like the multiple effect evaporators. Okay?